So to recap, you have these two parallel plates, and then in between them, here's our oil drop, and that oil drop has some number of extra charges on it. So it picked up some extra electrons. 1, 2, 3, something like that. So because we have charged plates, our electric field is pointing downward here. And this is a negative charge, so it's going to be attracted to the positive plate and repelled from the negative plate. So the electric force it's going to experience is going to be upward. Ooh, rainbow force. That's the electric force. Big F. Fe. It also has the force of gravity pulling it down. Fg, force of gravity. And when those two things are balanced, then this drop is going to stand still. Okay, and that's really what they were going for, because they could figure out the force of gravity on this thing. So when the charge is balanced, they could figure out the force of gravity, and that would mean that the force of gravity was equal to the electric force. And the force of gravity is mass times 9.8. The electric force is charge, Q, times the field strength. All of these things except for the charge were known, or they could calculate them at least. So the mass on this drop, they could figure it out because they could measure the size and they knew its density. G is 9.8 meters per second squared. The electric field strength, they were controlling that using their voltage device, their voltage source. So all they had to do was solve for Q. And it turned out that it was always some sort of multiple of 1.6 times 10 to the negative 19. Okay, and so he saw all of these things, 6.4 times 10 to the negative 19, 3.2, all of those are just multiples of 1.6 times 10 to the negative 19 coulombs. And so he determined that must be the charge on one single electron. So we can do these calculations ourselves, just as a sample of what he had to do. So in a Millikan experiment, an oil drop had a mass of 2 times 10 to the negative 15 kilograms. It had a charge of positive 2 ECs and was in an electric field of 140,000 newtons per coulomb up. What was the acceleration of the drop? Okay, so here's the situation. We have our parallel plates like this, upper plate, lower plate, and it says that the field is pointing upward. Okay, and so we've got a drop here in the center. It's not moving, or is it? It's asking us for the acceleration of the drop. Okay, that's this part over here. What's the acceleration of the drop? So this drop actually might be moving. This doesn't say that it's held in balance. During the experiment, the point was to hold it in balance, but this particular question is really just asking us to figure out the acceleration under certain circumstances. Okay, so we know that this thing has a positive charge. It says plus 2 ECs, and if the field is pointing upward, that means that this must be the positive side, and this must be the negative side. Okay, we should be able to figure that out. So the field points in the direction of the force on a positive charge. So a positive charge would experience an upward electric force. Okay, we have a positive charge over here, so it would be repelled from the positive side, so that's pushed upwards, and attracted to the negative side, which was on the top. So if the field is pointing upwards, that must mean that the bottom plate is positive and then top plate is negative. Okay, so now we have the electric force, which is going to be pushing upward, and the force of gravity, which is going to be pulling downward. and we don't know that they're balanced. So here's the force of gravity. This one is the electric force. And we're supposed to figure out the acceleration. So we're going to use F net equals ma to figure it out. Okay. So inside F net, the forces that are acting in the up and down direction on this charged oil drop, were the electric force up and the force of gravity down. Now, we don't really know which way it's actually going to be traveling, so we just have to name either up or down the positive one. Okay? So let's just say that up is positive and down is negative. You could have chosen the other way if you wanted to, and it will still work out just fine. So our electric force is going to be the positive one. Our force of gravity is the negative one. And together those things equal mass times acceleration. Okay, now our electric force is Q times E. And our force of gravity is mass times 9.8. And then on our other side, we still have mass times acceleration. Okay, now if we look through the question, the things that I can see that we are told are the mass of the drop, the charge of the drop, the field, and we are missing the acceleration. So if we look through our formula over here, we have figured out, or we're given the charge, we're given the field strength, we're given the mass, we know the 9.8, and this is also the mass. So the only thing that's missing is the acceleration. So we have to do some algebra to get that thing by itself. So if we're trying to get the acceleration by itself, I need to divide by mass. That's the only thing. Okay, so my next line over here is going to be Q times E minus mass times gravity divided by mass equals the acceleration. Okay, so I've done the algebra now, need to put in the numbers. So my charge is 2 ECs. So I notice in my question that my units of charge are ECs and my units of field strength are newtons per coulomb. So the coulombs and the ECs, they don't match. I can't put them in the same equation. So I need to convert one of them. The easiest way I would say is to change the ECs into coulombs. So 2 ECs get rid of the ECs, change it to coulombs. 1 coulomb is 6.25 times 10 to the 18 ECs. And so I get from there 3.2 times 10 to the negative 19 coulombs. So there's my charge. So now I'm going to put that in my formula over here. So Q is 3.2 times 10 to the negative 19 coulombs. My field strength is 140,000. There you go. Newtons per coulomb. My mass is 2 times 10 to the negative 15 kilograms, and G is 9.8 meters per second squared. Okay, that's my top side. Divide that by my 2 times 10 to the negative 15 kilograms. And that gives me, I'm going to put it down here, that gives me my acceleration. And when I do that calculation, I end up with 12.6 meters per second squared. 12.6 0.6 meters per second squared. And my answer was positive, and I said at the very beginning that positive was up for me, so my acceleration is going to be up. So that means that the field strength is much stronger than the force of gravity in this case. Example 2. An oil drop with a charge of positive 3 ECs is in an electric field of 240,000 newtons per coulomb up. It is held in balance. What is the mass of the drop? So what we're looking for first, this says it's held in balance. Okay, so our starting point is that the electric force pulling up and the force of gravity pulling down are going to be the same. So here's our oil drop. We know that the force of gravity is always pulling down, and so that means that if this thing is held in balance, the electric force must be pulling it up. Okay, and again, being held in balance means that the electric force is equal to the force of gravity. That's our starting point. And then pretty much all of these questions work very similarly, that you expand each of those terms into their formulas. QE equals mg. There are 4 pieces. And then we look through the question for the pieces that we have. So we are given the charge. That's in ECs, so we should probably put that in coulombs. We're given the electric field strength. We are not told the mass of the drop. Okay, we always know that G is 9.8. Okay, so we're trying to solve for M. So we're going to divide by G, mass times 9.8, divide by 9.8 to get the mass by itself. So we end up with mass equals Q E over G. Okay, now we want to put all our numbers in, but our Q is in ECs, and so we need to change that to coulombs. So Q is positive 3 ECs. So we take 3 ECs, do our conversion. So get rid of the ECs by putting it on the bottom. 1 coulomb is 6.25 times 10 to the 18 ECs, and that gives us 4.8 times 10 to the negative 19 coulombs. So now we're just going to put all our numbers in here. So Q is 4.8 times 10 to the negative 19 coulombs. E is 240,000 newtons per coulomb. And then G is 9.8 meters per second squared. And that all put together should give us the mass. Okay, and so for the mass, you will get 1.2 times 10 to the negative 14 kilograms. The last one is the same idea as the other two. This one says that the electric field is what we're looking for. We're given the charge, we're given the mass, and it's held in balance. So if it's held in balance, we know that the electric force is equal to the force of gravity. Electric force is Q times E. The force of gravity is mass times 9.8. And we're asked this time for what's the electric field. So to solve for the electric field, we're going to divide the other side by Q. Okay, it gives us the mass in kilograms, so that's all good. This is 9.8, and the Q is 5 ECs. So we need to change our 5 ECs to coulombs. So you get 8.0 times 10 to the negative 19 coulombs. So then we can figure out our electric field strength. E equals mass, which is 8.0 times 10 to the negative 14 kilograms times 9.8 meters per second squared divided by the charge, which is 8.0 times 10 to the negative 19 coulombs. 19 coulombs. So our field strength then is 9.8 times 10 to the 5 newtons per coulomb. That needs a direction. Okay, so let's look back at the question. It's the drop is held in balance, which means force of gravity is down, electric force is going to be up. So the electric force is up, Fe is up, and the electric force, or the electric field, points in the direction of the force on a positive charge. So this is a positive charge, and so a positive charge means that the force and the field are going to match each other's direction. Okay, so that means that our electric field is going to point up. 9.8 times 10 to the 5 newtons per coulomb up. That's our field strength. You could have also done this in newtons per EC. There's no rule against that. And in that case, instead of doing the conversion, you would just leave this coulombs part as 5 ECs. And if you did that, your field strength would end up as 1.6 times 10 to the negative 13 newtons per EC, also up. Okay, both of those work totally fine. So you could have just left it as 5 ECs and not done the conversion, but then your units for field strength would be different.